So we're going to talk about pathfinding with breadth first search today, and it's going to be everything that you need for. Let me pull up the assignment. Come on, load. Everything you need for LT5. Where is it? LT5, which is computing the shortest distance between two tiles on the map while avoiding walls. LT6, finding the closest player while avoiding walls. So given all the players in this AI's location, which player is the closest while avoiding walls? So if I take walls into consideration, which player is the closest? So there might be a player 2 tiles away, but if there's a wall in between, there's probably going to be another player that's further away physically, but closer when you consider that you have to move around walls. That's LT6, and then AO1, the big pathfinding objective, where given 2 locations, given the state of the game and called from an AI player, so you know which player this is, find the path to the closest player that this AI should follow to be able to move towards the closest player is AO1. All 3 of these objectives are very related, and with today's content, you'll be able to do all 3 of these. You'll be able to finish the homework and finish AO1. And actually, AO2, you already have the content that you need for this one. You could have done that a while ago, but it's trees, and it's pretty complicated. That's why it's AO2. It's a bit tricky. So today, after today, you could finish up this homework, and even if you don't want to do LT6, with LT5, cut loose with your 5 out of 6 LTs and be done with CSE 116 projects. You're well within your right to do that. But after today, you'll have all the content to be able to finish this project. It's really the last content of the course that you'll really be asked to implement. Yeah?
I just had a quick question. So
yeah.
With this project, it said we only need to complete 5 of the 6 electric tasks, correct?
Right.
To complete the application objectives, I'm assuming you would suggest to complete all 6 of them, or would you need all 6 of them to complete the application?
Yeah, you should. You don't have to, but you should. And I guess it depends on which LT you skip and how you skip it. Like if you skip it because your testing is a little weak and one of my incorrect solutions you're not marking is incorrect, but you have all the functionality, you could still move on to AO1 and AO2 and get those done. But if you, especially if you don't know how to do LT6, if you don't get the functionality for that, it's going to be really hard to do AO1 without that functionality because LT5, LT6, and AO1 all build on each other. So if you can't get LT5 and 6, you're not getting AO1. Aside from some stroke of luck. But if you skip LT4, do 5 and 6, you can certainly do AO1, and then try to get AO2 without LT4 would be possible. So it all depends on the specific situation, but of course I would recommend getting them all done. But if you're banging, my way of saying, me saying 5 of 6, that's my way of saying if there's that one last incorrect solution you just can't get, let's not go through that. I already put you through that 3 times. Let's not do it again. I'll just let you cut loose after that one. All right, let's talk about pathfinding. So LT5, we just talked about it, but distance, avoiding walls. So given 2 grid locations, what's the distance between those grid locations while avoiding walls, without allowing any movement through walls? That's what we want to be able to solve today. And like I said, you'll be able to do LT5, 6, and AO1 with today's content. So quick refresher on paths. Paths is a sequence of nodes where each adjacent node in the path is connected by an edge. And the length of a path is the number of edges in that path, or the number of nodes in the path minus 1. So this Lincoln to MIT to Utah to SDC to RAND to UCSB to SRI is a path of length 6 in this graph. It's a valid path because all adjacent nodes are connected by an edge. Every time I move from one node to the other, I was able to cross an edge to get there. So that's a valid path, and it's a path of length 6. Let's throw another definition out there. Distance, and this is the one we really care about, especially for the homework. Distance is the length of the shortest path between two nodes. So to compute distance, to do it manually, just staring at this graph, we're going to take two nodes, Lincoln and SRI. Lincoln, SRI. We saw that there was a path that goes around the long way, but there is a shorter path. There is a shorter path from between Lincoln and SRI. If we go through MIT, Utah, SRI, we can find a path of length 3. We can look at this all day. We're never going to find a path of length 2 or a path of length 1. So the shortest path that we can find is length 3. So we say that the distance between Lincoln and SRI is 3. It takes a minimum of 3 edges to get from one to the other. We can have distance of 1. Rand and BBN, for example, are connected by an edge. We had to travel that edge to get from one to the other, but it's only one edge. Path of length 1 is the shortest path between these two nodes, distance 1. So distance, very important measure. Stanford and UCSB, let's do one more. We can go through SRI, 1, 2. We can go through UCLA, 1, 2. We have a couple paths of length 2, but no matter how hard we try, we're not going to find a path of length 1. So the distance between those two nodes is 2. Distance, very important measure, and in fact is exactly what you need to compute for the lecture test. You need the distance, avoiding walls. And of course, we're going to use graphs and BFS to get this done. All right, so we know what paths are, we know what distance is, we know what graphs are, we know what nodes and edges are, we know what adjacency lists are. We've talked a lot about graphs. Let's bring it on home and do some actual stuff with graphs. So let's use BFS to find the distance between two nodes, which is exactly LT5. Use BFS to find the distance between two nodes. So let's see how we can use this algorithm to extract important information that we're concerned about. And then at the end, I'll show you how to tie it into the homework if you want to know immediately. I do have a method in the homework, in the handout code, that will take the state, the game state. There's a method in the game state that will convert the grid into a graph. Something I used to have the class do, but I backed off a little bit on that one because it's just kind of tedious and it doesn't have to do with your understanding of graphs that much. Call that method, and that'll give you a graph that represents the game map. So you can represent it as a graph, run BFS on it, do what we're about to see, and then compute those distances, use distance to find the closest player, and then for AO1, use breadth first search to compute the path between the player and the closest player to the AI. So let's see how to do this. We're going to run through BFS again. I'll skip the details, and I'll skip the code. You have the code, and again, you'll have to modify that to do this kind of stuff that we're about to see. You'll modify the BFS code that I gave you. And let's run through this again and see how we can use this to get those distances and eventually those paths. So let's choose a different starting point this time because I'm sick of starting at UCLA. Let's start at Carnegie and run through breadth first search. And as I run through this, I'm going to build another graph showing only the edges that I used to explore new nodes. So I'm going to put Carnegie right up at the top. So over on the right, I'm going to build that graph that shows all of the paths that were taken during BFS. Start with Carnegie, and then I'm going to explore all the neighbors of Carnegie, Case and Harvard. And I'm going to draw these going down. Carnegie at the top, neighbors going down, and whenever I explore new nodes, I'm going to draw those edges going downward on the slide. So Carnegie, I explored Case and Harvard. When I explore Case, I'm going to find Lincoln. Harvard, I'm going to find BBN. So I'm traveling these two edges. I'm going to add those to my graph over here. I'm going to continuously repeat this process until I've explored all the nodes in this graph. At this point, we're going to have a decision to make. When we explore MIT, we could actually explore it from Lincoln or from BBN. And we're going to break that tie. We're going to choose an edge arbitrarily there. In our code and our implementation, it'll just depend on the order in which they were in the adjacency list and the order in which they were added to the queue. At some point, that decision is just going to be made for us. Either one is perfectly valid. It's not going to break any of what we're doing with distance and pathfinding. That's saying there are two valid paths to MIT, which happen to both be length 2, which will be important. So I'm going to say let's explore MIT through Lincoln, just because it balances the slide a little bit more. If they were both hanging off of BBN, I don't know. Visually, I wanted it over here. BBN explored Rand, but this edge isn't going to be in our graph on the right. So some edges are going to be excluded from the graph on the right. Keep going. MIT is going to explore Utah. And Rand gets to SDC, UCSB, UCLA. It's going to explore all 3 of those. UCLA is going to explore Stanford, and SRI can be explored through any of these 3 nodes. So we're just going to randomly choose which one it's explored from. I chose Utah, UCLA gets Stanford, and we have a brand new graph that's going to show the edges that were traversed during our run of BFS. So these edges that were not used are removed. Other than that, it's the same graph. And this graph happens to be a tree. The way we excluded edges, we don't get any cycles. So it happens to be a tree. We're not really going to use that information. But it does happen to be a tree. There's no cycles in this graph with the edges that we removed. Importantly, what we are going to use is that there's levels to this thing. The way I drew this visually, where every time you traverse an edge, you go down visually on this, what I was doing was going down to a new level, or at least what we can call levels and what we can label levels, starting at level 0 for the root, and then every time we travel an edge, we're going to increment the level number by 1. The level number of a node is the distance from the starting node to that node. You can go through this graph and verify all of these distances. From Carnegie to itself, distance 0, we're already at that node. We don't have to travel any edges to get from a node to itself. The path is length 1 node, 0 edges, 0. Case in Harvard, the edges, the nodes connected to Carnegie by 1 edge, they better show up on level 1, and of course they do, because that's the way BFS is exploring this graph. Any node connected to a level 1 node must have a path from Carnegie through that node to that node, through the level 1 node to the level 2 node. All those nodes are distance 2, and so on. All the way down to SRI and Stanford. You can look at that graph for days and days and days. You're never going to find a path from Carnegie to SRI or Stanford with fewer than 5 edges. This is a property that BFS guarantees. If we're careful with the way we run BFS and we track this information, we get the distance from the starting node to every other node in the graph. So for your lecture tests, you're trying to find the distance between 2 nodes. You run BFS on one of the nodes. Keep track of the levels. When you reach the other node, whatever level it is when you reached it, that's what you're returning. Or run all of BFS, get the level for every single node in the graph, and then look up the node for the endpoint and say, whatever distance you were, return that. So we can use BFS to find these distances, and if we're careful with the way we construct the graph, we're not going, for the homework, to relate to the homework, a node for a tile which is a wall either isn't going to be in our graph, or it's not going to be connected with any edges to any other node. So BFS will never travel through walls. It's only going to travel where there's an edge, which an edge is only going to be a valid path that can be taken by a player in the game, i.e. not into a wall. Run BFS on a node, or on a grid location, and then find all those distances, and find the distance to the target grid location. So we're using BFS and using this property of BFS to get the distance between any two nodes in the graph. It's all well and good, but during that explanation, I was like, well, I'm just going to draw them visually going down. How the hell do you do that in code? So let's talk about how we're going to actually represent that in code, because in code, you can't write a line of Scala that says, make it go down on the slide visually. That doesn't really make sense. So we understand the concept now. Let's see how we're going to track this in our code and how we're going to keep track of these levels as BFS runs. So for this, we're going to use a data structure. I say data structure to leave it to the reader to find out, but I can just spoil it. That's a map. It's a map of strings to ints. And we want to track for each node the distance that it has as we're exploring it. And we can initialize the starting node to a distance of 0. We know that the starting node has distance 0, so let's just get that one out of the way and pre-populate this map with that node in it. And then have just some default value for every other node. I have infinity here because we haven't explored that node. If any node isn't explored, that means there is no path from the starting node to that node. So it would effectively have infinite distance. You can't ever get there. In your code, if you want to initialize to -1 and have that indicate the lack of a path, that's fine too. However you want to represent it, but populate the data structure with something to indicate that we have not explored that node. So we start at Carnegie, and now whenever we explore a node, whenever we're adding a node to our queue and marking it as explored in our run of BFS, and here's the queue that we're going to order nodes in. Whenever we add nodes to the queue and mark them explored, if they're marked orange, they're explored visually here. That means they're in that set of explored nodes if they're orange. And then this is the queue for BFS. I'm going to add Case and Harvard to the queue. Whenever I add a node to the queue, whatever node I was exploring when it was added, I'm going to look up that node's distance, give it a +1, and that's the distance of those nodes that I just explored. So we're going to go to our queue and explore the next node. I'm going to look at Case. Case is going to find Lincoln. So I'm going to mark Lincoln as explored, add it to the queue, and update my map. Lincoln, what's its distance going to be? Well, it was explored from Case. Case had distance 1, and if I had to travel in one edge to get from Case to Lincoln, well, Lincoln's distance must be 2. Or if you want to think of levels, Case is on level 1. If we explored from a level 1 node to another node, that next node must be level 2. So whenever we explore a node, increment that distance, update the map. Oh, and I guess I kind of misspoke there. In your code, this would be a map of int to int, because we're going to always work in our nodes as the int IDs, not the strings. Next, we're going to explore Harvard. We find BBN. Harvard was distance 1. BBN is going to be distance 2. And here's where the ties are broken arbitrarily. It depended on how the adjacency list was ordered here, but we end up exploring Lincoln before BBN because it was added to the queue first. If Carnegie had Harvard, then Case, then we would have went this way first, but it was Case, then Harvard, we go the other way first. It doesn't matter because it's going to get the same distance anyway for our purposes here. But we're going to get Lincoln, explore MIT, Lincoln, distance 2, MIT, +1, distance 3. So every time you explore a node, you're going to add it to the set to mark it explored. You're going to add it to the queue to make sure that we go visit that node's neighbors. Whenever you do that, take the distance of the node you're exploring the neighbors of, find its distance, +1, that's the distance of the next node. So with one data structure, with a nice use of a data structure here, we can keep track of all this information instead of saying just draw it visually lower on the slide without doing something like that. BBN is going to find rand. BBN was 2, rand is 3. MIT is going to find Utah. MIT, distance 3. Utah, +1, distance 4. Rand is going to explore 3 nodes. Rand was 3. All 3 of those nodes we just added, that we just explored and added to the queue, all distance 4. So we're using 3 different data structures here. This is where we really get to leverage data structures and combine these in different ways. We're using our queue, we're using a set, which I didn't really introduce that much. We're using a set, and we're using a map to be able to run BFS while extracting important information, this distance information. Going to explore Utah. And just a reminder, Utah, MIT, and SDC, we are going to consider, but we're going to see that they're already marked as explored. Visually, they're orange. And in the code, we're going to say if the set contains these nodes, we're going to skip over them. So we skip over them. SRI is not explored. We're going to mark it explored, add it to the queue, and update its distance. Utah, distance 4. SRI, distance 5. UCLA is going to find Stanford with distance 5. And we have these nodes in the queue. We are going to look at all of their neighbors, but all of their neighbors are already explored. So we're just going to start ripping them out of the queue. Boom, 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 empty queue. Algorithm's done. And we have the distance information in this data structure, in this map, of all of the distances from UCLA to any node in the graph. This is a very key concept for LT5, LT6, AO1. So if there are any questions, I want to take a good pause here, see if there are any questions about this. Make sure we all get what's going on. Why do we go Carnegie to Case versus not Carnegie to Harvard? It's arbitrary. So from Carnegie, when we first started, we're going to explore Case and Harvard and add those both to the queue. This is completely arbitrary. It just matters. It's going to depend on how they're ordered in the adjacency list, which just matters like what order did you add the edges. When you're creating the graph and you call add edge, it just matters which edge you added first. That's going to end up being the deciding factor here. It doesn't matter either way for our distance and eventually our pathfinding purposes. Technically, you'll find a different path to MIT. Like when we get here, our AI is going to end up traveling this path rather than this path in our pathfinding algorithms, but both paths are length 2. So either path is equally valid, is equally the best path for our purposes. They're both going to be distance 2. For example, if an AI is going diagonally 1 tile, it can either go up and across or across then up. It's effectively the same decision that we're making here. It doesn't matter either way for our purposes, and the tie is just broken arbitrarily just by the way things happen to be ordered. But it is effectively the same according to what we're doing, according to our end goal. What's the queue being used for? The queue is this queue in the code. So that's this queue in the code where we're going to add, starting with our start ID, we're going to add that to the queue. And then each time we explore a new node, we're going to enqueue that node into that queue. That's exactly this queue in the code. And then anything that's marked in orange, that means that they've been added to this set. So whenever we explore a node, we're going to add it to the queue and mark it as explored. And then this is where you would modify this code. You would add a third thing there, add your new data structure that says, okay, this node that I'm exploring, this node here, is going to have whatever the distance of this node is plus 1, and update that data structure. So you want to create a third data structure here, and then update that data structure down here. But this is the queue. I went a little beyond that question, but this queue right here. That's the queue. That's the queue that I'm visualizing up here. It's for queuing. Thanks, Trevor. Anything else? Those are good questions. Is that making sense? It's got to be at least one of you who's confused. I want your questions. If not, I'm just going to steamroll right into pathfinding, if everybody's good with this. Right, doing it. Oh, unless Cole has a question. We're all going to wait for Cole. Did I scare you? No, I was just stretching. Well, I saw you were typing too. Or were you stretching your keyboard muscles? It's another real-life example where we could use BFS and distance. It's a good question. I would struggle to think of another non-pathfinding example off the top of my head, but like if you wanted to find the closest path, like how to get to your next class most effectively, if you somehow map the campus into like 1 foot by 1 foot squares and then mark where all the walls are, you could use the same idea to like get to your classes. I don't know, that's pretty much the same thing we're doing on the homework though. Google Maps, not quite. So Google Maps, you would have to do the same thing though. You'd have to break things down. So one of the limitations of BFS in terms of pathfinding is that it can't take the notion of an edge weight into consideration. So if the edges have different weights, for example, with directions, you would mark all the intersections, and then the edges would have weights, which would be the distances, or rather the time that it takes to get between those two intersections, because not all intersections are equal. With BFS, you're just going to minimize the number of intersections that you have to go through to get from point A to point B. So we do need some more power before we tackle something like that. That's why I was careful to say with the campus you would have to break everything down into like 1 foot by 1 foot blocks. That's why the game works on tiles. We have to do that kind of stuff because BFS has limitations like that. If we want to take edge weights into consideration, that's 331's territory. That's Dijkstra's algorithm. If we want to take negative edge weights into consideration, that's Bellman-Ford, which are both algorithms you study in 331. So there are ways to do that. It's beyond 116. I'd be happy to talk about it. If somebody wants to talk about those last 2 weeks, those review weeks, I'd be thrilled. But it's outside of what we need to think about for 116. And A star is an algorithm. I'm thinking of the right one, right? A star is an it's not the right word. It's Dijkstra's algorithm is a specific implementation of A star. So Dijkstra's is very similar to that. A star just uses different, I'm blanking on the words now, different, it's right there, but I can't think of the word. Blanking on it. But it's a little more efficient than Dijkstra's in certain applications, but not asymptotically so we don't really care about A star in 331. It's just more complication for no asymptotic gain. So it's just more confusion for students for no theoretical gain that the class is concerned about. But it is interesting. I'm sorry, that's bugging me too much. Heuristics. With different heuristics. So with Dijkstra's, all edge weights are considered the same. With A star, you take extra information into consideration to modify the edge weights a little bit. For example, how far away are you from the starting location? How close are you to the destination? And it takes those heuristics into consideration. Yeah, we can I'll have to add a homework to 116 someday that you do my taxes. It would be a good homework one, just do my taxes kind of thing. Not specifically mine. Maybe I could give some data to fuel the thing. But like, computing taxes is good. It's a good thing. And it's notorious in 250. What's my SSN I need for your taxes? All right, when we start talking taxes, I know it's time to go on. BFS and pathfinding, distance is cool, but that gets us through LT5. LT6 is just iterating through all the players, finding the distance from the particular player to all other players, and then taking the min. But for AO1, what we really want is pathfinding. How do we actually find a path out of this? Well, it's actually not going to be too crazy. I've said this a few times already, but the jump from LT6 to AO1 in this is fairly small. If you can do LT6, you can do AO1. We're going to use an extra data structure here, except now we're going to use it in a slightly different way. Instead of using it to just track distances, we're going to track the previous node itself and then use that information to build the paths after we're done with the algorithm. Or did I miss an actual question? Oh, because they just ripped real quick. So for computing the distance, every time you add something to the queue, you would take the most recent entry and map it to the length of the queue minus 1. Right? Wait, hold on. Let me make sure I'm understanding. Length of the queue minus 1. No, you don't take the length of the queue at all. But when we dequeue, we're going to go through this part of the code. We're going to dequeue from the queue. We're going to take whatever in the front of the queue and explore the neighbors of this node. We're going to grab all the neighbors of that node from the adjacency list, and for each one, we're going to explore that node if it has not already been explored. When we explore it, we're going to enqueue it, add it to the set to mark it as explored, and update the distances graph. So we have two nodes. When we're inside this conditional, we have two nodes. The node where we're coming from, and then the node that we're going to, and we're traveling across one edge in this adjacency list to get from this node to this node. So we're exploring this node's neighbors, and this is one of the neighbors of that node. So when we update the distances, we're going to look up the distance for this node, add 1 to that. That's the distance of this node. Because we already know the closest distance from the starting node to this node. That's going to already be in our table by the time we get to this point, because we always add that to our data structure when we're enqueuing a node. So if we're dequeuing this node, we already know the distance from the starting node to this node. We have to already know that, because how the hell are we dequeuing it if we never enqueued it? And when we enqueue it, we're always updating its distance. We know its distance. So if we're dequeuing it, we know this node's distance. We're going to look that up in the data structure that you're going to add during LT5. Hit it with a +1, and then update that table for this node. Add its distance to that data structure and say, whatever node you were explored from, add 1 to that, and that's this node's distance. So now we know this node's distance as we're enqueuing that node. So like for the very first node, the start ID, we're going to initialize this to be 0 distance to kind of give everything something to hook onto to start everything. We're going to dequeue the starting node. That's going to have distance 0. And then any node that we explore from the starting node is going to have 0 plus 1, 1, distance 1, that we're going to add to that table. But we never take the length of the queue into consideration. The length of the queue is going to change in ways unrelated to distance throughout the run of this algorithm. For example, when we that's a good example. For all of these nodes, the length of the queue was 2 for a very long time. Length of the queue was 2 for a long time, but we have nodes of distance 1, distance 2, distance 3, distance 4, all different distances. The length of the queue doesn't factor into anything. In fact, a queue, we can enqueue, we can dequeue. We can't even ask a true queue, for its length. We don't even know that information. The dequeue is in the Scala library. I think I used my own queue for this. I used the one in the one that we saw in class. You could use Scala's queue too. Shouldn't hurt anything. But I used the one that we built in class. Enqueue and dequeue, those are the second lecture for linked lists is when I went through stack and queue. Those are the two methods we saw for queue, enqueue and dequeue. Enqueue adds something to the back of the queue. Dequeue takes the first element, the next element that's at the front of the line, front of the queue, and removes it and returns it. Yeah, no problem. Well, I think you were saying thanks to Nicholas, though. Oops. All right, let's do some pathfinding. So we saw how to do distances. Let's just modify what we're going to store in this data structure just a little bit and use that for pathfinding instead of distance. What we want to do is remember all the paths, all the edges that we traverse as we add those edges. So we're going to initialize the starting node just to something, to anything that's not going to be interpreted as a node. Since the nodes are integers, like I said for distances, I always like -1 as a value. Make sure you don't have any node with an ID of -1, and then you can use -1 fairly safely to indicate a special type of information. -1 means this is the starting node. We don't store anything meaningfully for that node. Or you want to do like infinity or min value or something, whatever you have to mark that as a special node, a special case. Then for every other node, this would be my -1. Then for every other node, when we explore that node, instead of taking the node that explored its distance and +1 like we just did, we're going to store that node itself. So from Harvard, we're going to say, where did we find Harvard? We found Harvard through Carnegie. We found Case through Carnegie. We're going to explore, and I'm not going to put the queue up again, but we're going to explore Lincoln through Case. So Lincoln was explored from Case. Instead of looking up Case's distance and adding 1, we're just remembering that node itself. We're going to do this with the IDs of the nodes in our code. We're going to store the ID of that node each time we explore a node. Which node discovered you? That's what we want to remember for each node. MIT was explored through Lincoln, so MIT explored from Lincoln. BBN was explored from Harvard. BBN, Harvard. RAND was explored through BBN. So we're going to remember that information for every single node. For each node, we remember which node it was that explored that node, that first found that node, the node that added it to the queue, that marked it as explored. That's what we want to remember. It's the same logic that we did before, just a little bit easier. We don't even have to do any lookups and adding 1. We just remember the node itself. Just store that in that graph, or in that map. Now, when we want to find the closest path, the shortest path, or at least a shortest path, there are multiple shortest paths in this. When we want to find a shortest path, we're going to take the node that we want to find. So if we want to find the shortest path or a shortest path from Carnegie to Stanford, the start is always going to be the node that we want to come from. So we run BFS from Carnegie. That's our start of our path. When we want to find the shortest distance to Stanford, we're going to start at Stanford and build our path backwards. We're going to start at Stanford, and we're going to say, okay, we want to end up at Stanford. To end up at Stanford, which node do we have to have came from? Well, that's UCLA. Okay, so if we're at UCLA, where must we have came from to find one of these shortest paths? RAND. Okay, well, how did we get to RAND? BBN. Well, how do we get to BBN? Harvard. Well, how do we get to Harvard? Carnegie. How do we get to Carnegie? Well, that was the start, and we know we're done at that point. And as you're going through these, build your linked list, keep prepending those nodes, and you have your shortest path. So for each node, we just stored the node that explored it, and then when we want to find the paths, we start at the end of the path and go through our data structure working backwards until we get to that start node, whatever you used to indicate that this is the starting node. I like -1, use whatever you want as long as it's not an ID of a node in your graph. If it matches the ID of a node in your graph, you're going to go to that node and just go around in circles forever. Your path is going to keep, how did I even get that highlighted? Your path is just going to run around in circles forever. You're going to end up in a cycle. So once you see that special marker that you added that says this is the starting node, that's the start of your path, and you return that path. Here's your shortest path. Then it goes into your lecture task code from earlier, which says, okay, I'm here, and I want to get to the next spot in this path. Where do I go? And travel that direction. So if your AI player is at this node, it's going to move to the center of this node. Once it gets to this node, your path is going to be this path, go to this one, etc. So it combines with your code from the previous lecture tasks to be able to get this AI moving along that path. Then at that point, once you finish AO1, your AI is, they're pretty sophisticated. They'll hunt down the closest player. The closest player is often another AI, so the AI will attack each other, but you can get that functionality. You can see that functionality after AO1. You have pretty smart AI after that, which shouldn't get caught on walls. I think they sometimes do end up getting caught on walls, just the way we have things when they're trying to cut a corner, just the way things line up sometimes. But they're pretty smart about that. And they'll shoot, too. If you haven't gotten to that point, they'll be shooting at you, too. All right. Well, one big problem. We have a game. We have a grid, a 2D grid with tiles. How does that graph of the early version of the internet, how is that even going to help us here? Well, let's talk about it. So this is a different version of the homework. The graph used to look like this. It was more maze-like, and you would have to traverse the maze. Your code will be able to do the same thing. Your code's plenty powerful enough to handle this. But I just changed the actual, this is just a maze. I changed it to be an actual game. But how does anything that we talked about help us with this? Well, we're going to take this graph, or take this game board and turn it into a graph. So we're going to create a node for each tile, each game tile, each grid location, as I call it in the code. Each grid location is going to be a node, and that node will be connected to any adjacent nodes that are valid movements that can be taken. So between the walls, there's no edge between this node and this wall, or alternatively, you could just not add nodes for the walls at all, would work as well. But there's only going to be a path between nodes that are adjacent to each other and that have valid movements between them. So for example, we're not going to add an edge between this node and this node. That doesn't make sense. We're just going to add no edges between the adjacent nodes that can be taken. And then we run BFS on our starting node and then find that path to our ending node. And that'll be a shortest path between the two. And it doesn't matter, how much complexity we have in this graph. This should find the shortest path, which is this path here. It'll end up finding that path through this graph. It won't get stuck on any walls. It won't get caught in a corner. It won't explore any inefficient paths. It's going to find the shortest path to go to that end. So what we see when we're playing a game, we'll see this. What the computer sees, what the AI sees, what the algorithms see is this. They're going to see this graph. They're going to run BFS on this graph, find the shortest path to their destination, in our homework, to the closest node, or to the closest player, the location of that closest player, and then travel that path. Now add AI with guns to it? Yeah, I did. Your homework has AI that shoot at you. And that's how we're going to use all this graph stuff in the game to have AI that'll hunt you down and shoot you if you don't shoot them first. Yeah, the game actually has, I don't know if you were joking or not, but the game does have AI that shoot you. I mean, they're just circles, but if you want to envision them having guns, where them projectiles are coming from. And in the code, I do provide, I'm in my examples. Give me AI. In the maze. I mean, I could take the code for that maze, actually, and just slap it in homework 4. It uses all the same basic code, the same structure. Or you can, actually. Like I have this maps. I only have one level here. You can change this level to change where all the walls are. Where the enemy spawners are, where all the walls are. You can change this map into whatever you want. If you want to play around with things, which is always fun, you can make a different map just by changing this stuff. Or change it to a different level. I have it set up so you can have multiple levels, because this is code from towers where you have, each time you kill the base, you go on to the next level. So I have it set up for multiple levels. I just only have one in the handout code. That's not what I was showing. AI game state has a level as graph method that returns a graph of the level. This graph will contain all the nodes with IDs using this function. So if you want to cut and paste this function into your code, go for it. It'll use this function to generate IDs from the grid locations, the XY of the grid location, and create unique IDs for each grid location. And then this graph, you'll be able to take this function, whatever grid location you want to start at, use this function to get its ID, run BFS on that node, modify your BFS to return the map containing the previous node for each node. What node explored this node? Take the ending node of the closest player, use the same function to get its ID, and then go to that map and reverse through it to build your path, and that's your path for AO1. And this, did I say that? This will return a graph where each grid location is a node, and there won't be any edges to nodes that are walls. So you won't be able to traverse walls if you're running BFS on this graph. It'll be exactly what we saw in that last slide. It'll be that graph that the AI sees. This does not seem that efficient. It's actually not bad. It's fairly efficient. I think it's as efficient as it can be, asymptotically anyway. How do you use that? The methods take this as, I didn't give templates, but they'll take an AI game state reference, and then you just call it. I can do game state dot level as graph. Whenever you have a game state as an input, that's my way of saying you probably want that graph. And with that, we're out of time. So great hustle out there. Good job, everyone. See you Friday.